So section 9.1, two proportions. So there are times you want to test a claim about two population proportions or construct a confidence interval estimate of the difference between two population proportions. As with all other hypothesis tests and confidence intervals, the process is the same, though the formulas and assumptions will be different. And again, keep in mind that all those formulas and assumptions will be on your cheat sheet for this unit, so you do not need to memorize those. Alright, so these next couple pages here just outline the steps that we've seen before, so it's a reference page to come back to. So in this case, again, our first step in a hypothesis test, the P for parameters. So our parameters here, we're going to be looking at two groups, so we're going to have P1 and P2, and then from there we'll get these random variables P hat 1, and this should say P hat 2. And so again, this wording looks very much like what we've already looked at, only now we're talking about two different groups. Okay, our step 2 is setting up the hypothesis, which now we'll have P1s and P2s. So for a two-tailed test, we can test that P1 differs from P2. Or alternatively, that's the same thing as saying the difference is not 0. Or for a left-tailed test, we're going to test that P1 is less than P2. Or alternatively, that's the same thing as saying the difference is less than 0. And for a right-tailed test, we're going to test that P1 is greater than P2. Or alternatively, again, it means the same thing to say that that difference is greater than 0. In step 3, again, we're going to check our assumptions, which basically are the same as what we've had before, only now we've got to basically check them twice. So we need a simple random sample taken from population 1 and a simple random sample taken from population 2. We want to make sure that the samples are independent, so that they've not been paired in any way. And then there can only be two categories for each object, and again, the same for both samples. And then we need to have at least 10 objects in each category for both sets of sample data now. So that means we need x1 and n1 minus x1, and also x2 and n2 minus x2. All of those need to be at least 10. And then the last one, again, typically we're not given the population sizes, but if so, again, we need the population size to be greater than or equal to 20 times the sample size for both groups. So if those conditions are met, then we have met the conditions for this 2 prop Z test. So again, our test statistics starts with, again, first looking at the statistics and then the standardized test statistics. So in this case, we're going to have a P hat 1 and a P hat 2. So again, we're just going to be the same formula we've looked at before. Now it's just for two groups. And we're going to have this pooled sample proportion, where basically we're going to be throwing the two groups together as one. So that means our denominator now will be n1 plus n2 for the total number of objects, and then the successes, number of things in the group that we're category we're interested in, x1 plus x2. And then our standardized test statistic is the z-score, and our formula is given here for that. And again, remember, once we have this set up, we can just get that final value off of the output screen. Our sixth step is to obtain the p-value, so we're going to use technology to get that, whether that's our TI-84 or StatCrunch. And then once we have that p-value, we are going to again be looking at these pictures of the sampling distribution to make sense out of all of the values for our statistic, test statistic, and p-value. And then our seventh step is to make a decision. So again, same logic as before. We're going to reject HO if the p-value is less than or equal to alpha, and we'll fail to reject HO if the p-value is greater than alpha. And then we state a conclusion. So if we reject HO, so we throw HO out, that means there is significant evidence to conclude, and then we write HA in the context of the problem. But if we fail to reject HO, then that means there's not significant evidence to conclude, and again, we would fill in HA in the context that we have. Then the confidence interval for the difference between the two population proportions. So again, our first thing there is the parameters again, so that's identical to the previous page. Assumptions identical to the previous page. And so in this case, if the conditions are met, we have met the conditions for the 2 prop Z interval. So the next letter in panic is I, where we need our interval estimate. But again, from that we first start with the point estimate, the center of that, our interval that we're going to get. And again, we can get that information using technology, so whether that's our calculator or StatCrunch, our interval will be on that output screen. Again, our sample proportions that we had before, And again, the difference between those sample proportions, that is not actually on the output screen. So this we would actually have to take p hat 1 and subtract p hat 2 to get that value ourselves for the center of that the center of that confidence interval. And then the confidence interval is for p1 minus p2. So again, this is important that this is these are parameters here and not our random variables. And so that interval is given in the output of the technology. But then once we have that interval, so again, in the last section we only had one parameter, and so we would say things like we were 95% confident that the percentage of all objects in some category were between two endpoints. Okay, but now we're looking at the difference between proportions. And so if both of those endpoints are positive, we're going to say that we are whatever percent confident that the percentage of all objects from population 1 that are in some category of interest exceeds the percentage of all objects from population 2 that are in that category by a percentage between the lower endpoint and the upper endpoint. Okay, so now we're not getting proportions for the single populations, but the difference between those two populations. And if both the endpoints are negative, okay, then we're going to say that we are C% confident that the percentage of all objects from population 1 in the category of interest is less than the percentage of all objects from population 2 that are in the category of interest by a percentage between, and then these are absolute values here, the upper endpoint and lower endpoint in absolute value. That's just to make sure that we don't have any negative percentages here. The less than already takes care of the fact that we got the negative values. But if one endpoint ends up negative and one endpoint is positive, that means that we don't have any evidence of a difference between the groups. All right, so that's a lot of words and a little bit of some new context here. So we're going to back up for just a second and look at something simple with just numbers. So one way to compare two values is to subtract them and to see the difference, which is what we're doing in this section. We're subtracting parameters and looking at the difference between them. So although the order of this subtraction gives you a different sign for your answer, it does not give you a different answer when you include the context. So what do we mean by that? So for example, let's say that I have $10 and you have $4. So if we decide to subtract that as 10 minus 4, we get a positive 6. Well, this just means that I have $6 more than you do. But had we subtracted them the other way around, 4 minus 10, we would have gotten negative 6. And this just means that you have $6 less than I do. So although the order of subtraction gives us a different sign on our number, it does not give us a different answer when we include the context. The statements I have $6 more than you do and the statement you have $6 less than I do mean the exact same thing. So the order of subtraction actually does not matter when we include the context in a given problem.